Hello, everyone. Hey, it's time for a little more organic chemistry. And today we're going to start looking at reactions of alkenes. Okay, so just as a little heads up, there are several reactions that carbon-carbon double bonds can do. And you're going to need to know the reagents, have them memorized, and be able to predict the products. And so about this time, I know, lots to memorize, and it's a task. It's something that has to be done. It takes some effort, right? So I'll have students say, well, why? Why do we have to do this? So if I have to justify it, I guess the first thing I would say is, if you're going to think about being a pre-med or a chemistry major, that's the expectation. That's the standard. It's that you have to have these reactions memorized. You don't get notes on the MCAT, and they're just going to show you some reactions, and you have to be able to predict them, and you'll have to have known what the reagents are and how they affect an alkene. Chem majors, kind of same deal. It's expectation. Another way to think about it is if you go into the ER and you expect the doctor to know what they're doing, they know, the parts of the body, what's happening, different diseases. You don't expect that person to go and say, oh, you know what? That symptom looks familiar. Let me grab my phone and look up what symptoms and what possible diseases that might correspond to. No, that's not the expectation. No, you're in the ER. You don't have time to look up stuff. You need to have that memorized. So honestly, I think that's one of the reasons why medical schools require their pre-med students to do well in organic chemistry, because it's a memorization marathon. And if you can memorize this stuff, oh my goodness, you've trained your mind well and you're good at memorizing things. So you'll be ready. Your brain is trained to memorize stuff in medical school. That's what I think is going on. Anyways, here's another reason. Jokes just aren't funny if you don't have reactions memorized. Someone sent me this some time ago. It's a picture of vinegar and baking soda, and the caption reads, "You're playing a dangerous game there." Well, if you don't know that baking soda and vinegar do the old science, fair volcano experiment here, vinegar and baking soda creates carbon dioxide, and very rapidly too. So you make a neat little eruption there. And with just this much vinegar, and I don't know how much baking soda is in the sand volcano, you're getting quite an eruption there. So now, okay, now we understand what we're talking about here. This is a bad idea, putting so much baking soda next to so much vinegar. Okay. Anyways, flashcards work. There's phone apps that allow you to do flashcards. Do a little digging, and I'm sure there's been organic chemist students before you that have already designed a way to memorize these. So take a look on the web, see what resources you find, and send them on to me. See if something really works for you. I'll pass it on to the class. Okay, first reaction of alkenes. I decided to go with a class of reactions called electrophilic addition reactions of alkenes. Sounds pretty sciencey, pretty scientific here. Let's break it down. Electrophilic refers to electrophile. We learned in a previous video that electrophiles are things that seek electrons. Here we're talking about the reagents. They're seeking electrons, specifically the pi electrons of the alkene, right? The alkene has a carbon-carbon double bond. One's a sigma, but one is a pi bond. I'll pick the top one. And remember, sp2 hybridized carbon is trigonal planar, so the molecule is flat, and the p orbitals sideways overlap and position those electrons above and below the plane of the molecule. They're just out there. They're accessible. They're not the electrons are not in between the atoms. They're above and below the atoms. That's where the pi bond is. And that makes them reactive. They're just available, accessible. And so you have reagents say, ooh, I want those electrons, and they'll attack the carbon-carbon double bond. So as a guideline and general rule, alkenes are quite reactive. In fact, because they're so reactive, some of them are somewhat toxic. Okay, what else do we need to know about these reactions? Electrophilic, okay, the reagents seeking pi electrons. They're also addition reactions. That's actually a good pattern to remember. What's an addition reaction? Kind of review the old videos we saw about that. That's where you take all the atoms of the reagents and just mush them together to make one molecule. 1 plus 1 equals, sorry, 1 plus 1 equals 1. Okay, that's weird math. But essentially what you're going to do is take an alkene, an electrophile, and add them all to create one molecule. So here's how it kind of goes with a specific example. We have, what is this? This is 1 propene, 3 carbons of propane, but there's an ene. Let's start numbering on carbon 1. So this is 1 propene. That's the IUPAC name. It's also propylene, the common name. And what happens is when this alkene of propene reacts with HCl, the pi bond goes away. You get a single bond between those 2 carbons. And then if you remove the pi bond, wait, carbon makes 4 bonds. So if you take away a bond, that means each of these carbons, the alkene carbons, they're able to make another bond by removing the pi bond. And so it turns out an atom of H, an atom of Cl go fill the spots left behind by the pi bond leaving. Turns out nature, she makes the rules though. And in every case with propene, the hydrogen always goes to the end carbon and the chlorine goes to the middle carbon. You always make this isomer, the 2-chloropropane. You never see any of the 1-chloropropane in here. Again, nature makes the rules. It's up to us as people, scientists, to figure out why. But anyways, that's the pattern. Take away the pi bond, add the atoms of the reagent. And then you have to think about the right orientation. Okay, and then, sorry to say, this is not the only reagent that does this electrophilic addition reaction. Chlorine is one of the halides. Do I have a periodic table over here? Somewhere I do. Way over here? Yeah, I do. Chlorine is one of the halides. Found in column 7A are also bromine and iodide. So it turns out HCl, we saw, works. HBr also works. HI works as well. From general chemistry, I hope you remember that hydrochloric, hydrobromic, hydroiodic acids are strong acids. However, hydrofluoric, HF, is a weak acid. That hydrogen and fluorine make a stronger, somewhat covalent bond. The fluorine doesn't let go of the hydrogen as readily. It's a weak acid. And because it's weak, it doesn't work well in this reaction. So the chlorine, the bromine, the iodide acids, they work well, not fluorine. All right, so we got those 3 reagents. You know, so if you add HBr, well then the bromine goes on the second carbon. If you use hydroiodic acid, the iodine goes on the second carbon. Not a big deal. One of the things about hydroiodic acid is it's quite reactive, more reactive than HBr, more reactive than HCl. In fact, if it sits on the shelf too long, it decomposes. It's so unstable. Not so nice. Excuse me. So what typically is done is when you need to do a reaction involving HI, hydroiodic acid, it's easier to just make it whenever you need it. So it's very common to take some phosphoric acid, H3PO4, mix it with potassium iodide, and the phosphoric acid provides H+. Ki, potassium iodide, is an ionic compound providing I-, and then opposites attract. H+, I-, create hydroiodic acid. So one of those little glitches of organic chemistry, instead of seeing HI over the arrow, you might see H3PO4 and Ki there instead. And it's the exact same reaction. These 2 reagents make HI, predict the reaction as if it was HI. The hydrogen goes to the carbon on the end, iodine goes to the carbon in the middle. Nice. Someone saw this pattern That's how I think it happened. And they said, ooh, we got 3 strong acids, and the acids separate. H goes to the end, the halide goes in the middle. What if I take another strong acid, like sulfuric acid, make, add a little water to it to make the hydronium ion, which is a strong acid. Does a similar reaction take place? It does. So that's cool. Think of it as water. Yeah, water's a weak acid, I know. So you need an acid catalyst because only strong acids react. But to predict products, think about just having a water molecule over the arrow. And so what's the pattern? If it was HCl, split the H as H plus, put it on the end of the alkene. The rest of the molecule, the chlorine, goes in the middle. So now pretend you have water, take off the H, put it at the end of the chain, take the rest of the water, an alcohol, an OH group, and put that in the middle. Cool. So now we have 5 reagents for one pattern, one type of reaction. Again, it's all about the pattern. Lose the pi bond, split the reagent, put part of the reagent on one side, the other reagent on the other. Hydrogen goes to the end. But what if the double bond's in the middle of the chain? Or what if it's in a ring? What if there's some branches? Okay, it's going to need a little more work to find the pattern. Thankfully, someone else already did that. This Russian scientist named Markovnikov, his last name Markovnikov, he did a whole bunch of experiments with lots and lots of different alkenes with these reagents, and he deduced the pattern. He said, guess what? In every case, the hydrogen of the electrophile, that's the reagent, the H plus, goes to the alkene carbon that has more hydrogens. So let's relook at this one. The alkene carbons are here and here. The alkene carbon end has 2 H's. The alkene carbon in the middle only has 1 H. And Markovnikov's rule is the alkene carbon with more hydrogens gets the new hydrogen. So this carbon had 2. Afterwards, it has 3 hydrogens. And then what about the other alkene carbon? It gets the leftover piece. If it was HCl, it gets a chlorine. If it was HBr, it gets a bromine, and so forth. Students have the best ideas. So this is how I taught it. This is how I learned it. And maybe, I don't know if it happened when I was in college, grad school, or when I was teaching, but someone told me, yeah, Markovnikov's rule. It's basically the rich gets richer. I'm like, what are you talking about? Well, if you think about hydrogen like money, this carbon's more rich in hydrogen. It's got 2 H's. This only has 1. And in real life, if you want to make money, you got to have money. The rich are going to get richer. And that's what's happening here. Nature's no different. The carbon with more hydrogens gets another one. That's not fair. Yeah, but nature's making the rules. So we have 3 H's on this end. And the leftover piece goes in the middle. Let's try exploiting the pattern to predict some reactions on alkenes we haven't seen yet. So this is very much like exam mode here. So I know during this video and in future videos, I'm just going to randomly pick molecules, probably small molecules, so we can see the pattern more clearly. So I picked these 3 carbons with an alkene and say, okay, here's the product. We're studying it. You got it? See the pattern? Awesome. But I'm not going to give you this molecule on the test. I want you to apply this pattern to some new molecules. So here we go. Once you know the pattern, though, it's pretty straightforward. So on the exam, put yourself in exam mode, predict the products, that's the question. So what happens when this molecule reacts with HCl? And you go, I know this. Oh, yeah. Find the alkene, because alkanes are really stable. Carbon-carbon single bonds really stable. They don't react with acid. But the double bonded carbons do. The alkene group is reactive with acids. And the rich gets richer. Ooh, what's that mean? Well, here are your alkene carbons. How many hydrogens does this alkene carbon have? None. There's a double bond There's a bond down, another bond to the right and upward. This carbon, I see all 4 bonds, and they're the carbons. Carbon bonds 4 times, no room for an H. This top alkene carbon has 1 line to the left and 2 lines to the right. I see 3 lines. Oh yeah, but it bonds 4 times. There's an unwritten hydrogen here. This carbon has 1 H. This one has none. So the H goes here. I don't want to use a curved arrow because that's a reaction mechanism arrow. But that's what you're going to do. Move this hydrogen here. So copy your molecule and lose the pi bond. So the pi bond's gone. I like making little dots to represent where the alkene carbons are. The double bond used to be across here and here. The hydrogen went here. If you want to draw it in, that's cool. There's 1 H already, there's another H. But it is a skeletal drawing. So you don't have to draw in the H's if you don't want to. So here, maybe I'm not going to draw in the H's. Here I did. Your choice. When you're drawing the molecules, you decide how you want to draw them. But right now, this other alkene carbon is not an alkene anymore, and it only has 3 bonds. Had 4, but I took away the pi bond. So right now it only has 3. Well, that's room for the chlorine. So you decide where you want to attach it. It has to attach here, but you want to point it up to the down. I don't like putting it in a ring. It feels kind of crowded in there. So I'll put it here. But you can put it down here too. They're both the same molecules. Hey, we did it. We predicted the product. Using Markovnikov's rule and the pattern of lose the pi bond, add the atoms of the reagent. Okay, let's try this one. Here's the alkene carbon, and HCl. Ooh, so lose a double bond. So basically copy the molecule. Here's where the alkene carbons used to be. Lose a pi bond, did it, single bond now. And then who has more hydrogens? Well, this bottom one has 3 lines, so there's 1 H. This top one, dang it, has 3 lines, 1 H. It is a tie. So Markovnikov's rule says the hydrogen goes to the carbon with more hydrogens. Well, sometimes it goes down here. The chlorine goes up here. And sometimes it's reversed. There's no discrimination, no favoritism, right? Both carbons had 1 hydrogen, so sometimes the H of HCl goes to one of the carbons, and sometimes it goes to the other. And so you do have to draw both products to get full credit. This is what we see in the lab. You take, what is this? Trans, it's zigzagging, double bond, it's a trans group. The hydrogens are on opposite sides. The double bond begins on carbon 2. So this is trans 2 pentene. It then becomes 2 chloropentane and 3 chloropentane. And you get about equal mixtures, about 50-50 ratio in the lab. All right, let's try another one. So I took the same molecule up here. What is this? This is 1-methyl cyclopentene, and change the reagents. So HCl is now the hydronium ion. So what happens? Well, hydronium behaves like a water molecule that's splitting like HCl splits. So let's copy the molecule over. All the single bonds remain in place, but you lose the double bond, sorry, the pi bond. Who has more hydrogens? The top one. This one doesn't have any hydrogens. So the water molecule splits. Water came from hydronium ion, which is H plus and water. The H splits away from the water, goes to the carbon with more hydrogens. And then the leftover piece, the water, I'm sorry, it was water. The leftover piece is an OH group, an alcohol group, and it goes right here. And that's the product. Sweet. One more. Ki H3O4, H3PO4, you have to recognize that as doing the same thing as if you mixed in HI. Phosphoric acid, potassium iodide mixed together to create HI. That's the true electrophile, the true reagent. And now follow the pattern. Okay, so I copy the molecule and lose the pi bond. That's where the alkene used to be, over here. Well, the rich gets richer. Who's going to get the H of HI? This one? How many bonds do I see? This top carbon, I see one line to the left, one line to the right, two down, that's 4 bonds. How about down here? There's a double bond up, single bond to the left and down. There is then an unwritten hydrogen. This is the richer carbon. So the H goes here, and the iodide goes here. And that's our product. Cool. That's pretty powerful, right? So you can draw any alkene, even some that's never been made on planet Earth. Go in the lab with one of these 5 reagents, and you can predict what's going to happen with very accurate results. So that's one of the goals of organic chemistry, be able to make accurate predictions. Okay, now if on the exam, if I ask a short answer question, why do we only get the 2 chloropropane product and not the 1 chloropropane product? And you say, oh, it's the rich gets richer, or you say the alkene carbon with more hydrogens gets a hydrogen. That's not a reason. That's the pattern, but why? So be careful on homework problems and exam questions that are going to ask you to explain something. We got these little helpful guidelines. That's not a reason. That just helps us predict the product. The rich gets richer, and the alkene carbon with more hydrogens getting the hydrogen. Well, why? What's the scientific explanation? That's not explained by Markovnikov. Well, actually, Markovnikov worked on that too. But his rule is more of a predictive rule rather than an explanatory rule. To best explain how a reaction works, we need a reaction mechanism. We need curved arrows. So far in this class, we've done only free radical halogenation of alkanes. So you remember the initiation, propagation, termination steps? Okay, that was a mechanism with fishhook arrows because free radicals were involved. We had chlorine and bromine with a single dot, single electron. Okay, that was a radical mechanism. This one, however, is a polar mechanism. We're going to use a regular arrow with 2 barbs because 2 electrons are going to move at a time. And we don't have initiation, propagation, termination. That's really just for free radicals. This is a polar reaction. It's also shorter. Yay. Okay, so let's rewrite this propene molecule in a skeletal drawing just because it's easier. And then I'm going to get out of the organic chemist notation of drawing reactions where it's carbon molecule on the left, everything else above or below the arrow. Let's just put them back side by side like in Gen Chem, general chemistry. Okay, so how does this work? Well, first of all, if you're going to do this reaction, you're not going to do it in water. Why not? Hydrochloric acid is really soluble in water. Yeah, but water reacts with alkenes too. So we're actually going to mix hydrochloric acid that's pure. It's a gas. Propane is actually a gas. So we're going to need some specialized glassware to capture all these gases. But basically, you mix these 2 gases, give it some time. You might have to heat it up, but they will react. And so HCl in the gas phase has a covalent bond, as I've drawn it here. And if you want to, sometimes it's helpful to draw on the lone pairs when we do reaction mechanisms, because we might need one of these lone pairs. Actually, we are. Not in the first step, but we will later. Okay, so how does the reaction work? Well, after a lot of theory, a lot of experiments, this is what we figured out. The pi electrons actually make a bond to hydrogen. So these 2 electrons, 1 line equals 2 dots, right? So the pi bond, which I'm picking to be this line, 2 electrons, those 2 electrons are going to connect to the hydrogen. So the curved arrow is saying, yep, these 2 electrons connect to the H. The hydrogen can't make 2 bonds. So at the same time we have a new bond, the hydrogen, the old bond has to break. So these 2 electrons, 1 line equals 2 dots, 1 covalent bond is the sharing of 2 electrons. Yeah, Those electrons fall back on chlorine. Let me just put the hydrogen there dangling in the middle of nowhere for a second. Chlorine had 3 lone pairs, but now it has 4. Now, when chlorine has 4 lone pairs, it's an anion. That's the chloride anion. Okay, let's attach the hydrogen to 3 carbons here. So the 2 electrons used to be shared by this carbon and that carbon, carbons 1 and 2, but hydrogen can only make 1 bond. So it can't connect to both carbons. That's 2 bonds of hydrogen. So it has to go to 1. So we can either connect it to the end or we connect it to the middle. Whoops, the middle. It only can make 1 bond. So sorry, one of you carbons, you get to use these electrons to attach a hydrogen. The other one's going to be out of luck for a couple of microseconds or a certain short amount of time. If the hydrogen connects to the end, the plus charge goes here. The plus charge, oh yeah, because this carbon is only making 3 bonds. It's missing a pair of electrons. It's a cation. Cations that are on carbon are called carbocations. Yeah, clever name there. Carbon cation, carbocation. If the hydrogen attaches to the middle carbon, then the plus charge goes over here. Now, based on Markovnikov's rule, nature's already decided who gets the hydrogen. It's a carbon on the end. So it's actually this one and not this one. How come the carbon in the middle didn't get the H and the carbon at the end did? Well, it's not so much about where the hydrogen goes, but who has to bear the positive charge. In this case, the carbon in the middle has to bear the positive charge. It's short 1 bond, 3 bonds on a carbon with no lone pair gives it a +1 charge. Same true over here. If the hydrogen went the middle, then the carbon on the end is positively charged. It only has 3 bonds. So why is nature putting the plus charge in the middle of the chain? Well, you can do some other experiments with carbocations, and we discover a pattern. Here's some electrostatic potential maps of different carbocations. If you have a carbon with 3 H's with a positive charge, this blue color, blue tint, is saying there's a lot of positive charge all over the place. It's a strong carbocation. If you change out one of these hydrogens with a methyl group or any carbon chain, suddenly the whole thing's not as blue, it's not as sad, it's not as unstable. And that's because in the methyl group, there are 3 more covalent bonds, and bonds are electrons. So I know the methyl group has plans for those bonding electrons. It's to hold the H's to the C, but the molecule still has electrons in the molecule. And some of these electrons can creep over and kind of flow. They can't neutralize it, but can help. You say the electron density kind of moves over towards the carbocation. It flows that way to try and stabilize it. And if you take out one of the hydrogens, put a methyl group or any other set of carbons out there, the more carbon atoms with H's you have, the more covalent bonds you have, the more electrons are out there. And now look, we're getting some green and some yellow tints in here. It's not as blue anymore. There's more electrons. And the situation even improves further if you change out the last one and you have more groups out there. This is much more stable. It's not as blue, it's not as positive. It's still positive in the middle. Yeah, it's still a carbocation. But with more electrons around, it's stable. It's more stable. Let's classify the carbocation. This carbon is connected to 3 carbons, that makes it tertiary. This carbon is connected to 2 carbons, it's secondary. This carbocation, this carbon is connected to 1, that makes it primary. And then I don't have a 0 order, it's just called methyl. And that's the pattern we observe in nature. More electrons help more groups around the carbocation, makes it more stable. It's still quite reactive, don't get me wrong. Carbon doesn't like having 3 bonds. This is going to do something. It's going to react to try and get that 4th bond. But given the choice of who is positively charged, tertiary is the best choice. It's the most stable of these very reactive intermediates. Hey, Chem majors, if you want more explanation, here it is. The rest of the class, just kind of sit back and enjoy the ride. This is not going to be on my exams. But why? Why is that carbocation getting stabilized? Well, here's the carbocation on the left with the plus charge. The carbon that makes 3 bonds needs 3 orbitals for those bonds. It needs an S, a P, and a P. It's sp2 hybridized. And that means sp2, it still had a p orbital, it's empty. So we drew in the p orbital here, it's empty right now for the carbocation, the carbon with the plus charge. Next door we have a methyl group or any alkyl chain or whatever, and there'll be bonding electrons connecting the H to the C. And this is an sp3 hybridized orbital, right? This carbon's sp3 hybridized. So this is one of the sp3 hybridized orbitals. And electrons, these 2 electrons, are flying all over the place here. And they can sneak over here as they're attracted to the positive charge. And now instead of just staying in between these 2 atoms, they can kind of swoop out and actually be found anywhere in this volume of space. We have a larger molecular orbital. These 2 orbitals are overlapping. It's sort of making a bond. That's why the dotted line is here. This process is called hyperconjugation. And it's the mechanism, if you will, as how we think the carbocations are being stabilized. If you put a methyl group on this end, a methyl group on this end, you get more hyperconjugation, more electrons filling this empty orbital, and that makes it more stable. Okay, ride's over. Pick up your pencils again. Let's go back over to the mechanism. Kind of left you guys hanging over here. Okay, so why does Markovnikov's rule work? Because the more stable carbocation is created when the rich gets richer, when cation. When the hydrogen goes to the end of the chain here, this carbon is a secondary carbon, but if the hydrogen went to the middle, you make a primary carbon, and secondary is more stable than primary. Tertiary is even better, but there's no possibility of getting tertiary here. All right, we're not done with the mechanism. Nature then says, okay, I have these 2 choices, make the more stable one. Yeah, nature takes the route of least resistance, the path of least resistance. And then, after that, opposites attract. Carbocation has a positive charge, chloride anion has a negative charge. Just connect, bring these 2 together, make a covalent bond. So that you make a bond, you need some electrons. Hey, chlorine, you got 4 lone pairs. Why don't you use one of those to make a bond to the carbocation? Help a buddy out here. This carbon only has 3 bonds. Why don't you go make the 4th one? And that's what it does. And that's our product. Nice 2-step mechanism. I'm going to ask for a mechanism on the next test. I might ask for this one. And so what I'm going to give points for is, did you draw the secondary carbocation? Did you draw the Cl minus? Those are intermediates, short-lived products. They don't exist at the very end, but they temporarily show up. Did you give me 3 arrows? There's a curved arrow of the pi bond grabbing the H, curved arrow showing this bond breaking, and a curved arrow saying this bond is going to be made. And of course, did you draw the product? The right isomer, chlorine in the middle, not the end. I know, lots of details. That's what chemists like. We like all these details. Ooh, explain it to me. Cool. That's the reaction mechanism. Remember a minute ago, we said tertiary is more stable than secondary, secondary more stable than primary. Yeah, that's kind of important. Carbocations are really reactive. They actually don't form just willy-nilly. You need that powerful powerful acid to be able to make an alkene react to form a carbocation. I put these 2 close together. In certain cases, nature will see an opportunity to make the more stable tertiary carbocation, and sometimes she'll change the mechanism to make that more stable carbocation. Here's 2 examples to illustrate. And these 2 are going to illustrate the only 2 patterns we'll see regarding this new category called carbocation rearrangement. Okay, to keep it simple, let's keep the reagent the same, HCl. However, the pattern is going to be the same. The mechanism is going to be the same. We could use any of these 5, right? We could use HCl, HBr, HI. We could use these reagents. We could use hydronium ion. Oh, and where does hydronium ion come from? It comes from H plus and water. So maybe over the arrow, you might see H plus comma water, or you might see over the reaction arrow an H plus with water underneath. Or someone might be really clever. It's like, well, which acid produced the H plus? Well, maybe we use sulfuric acid. So you might see this over the arrow. And then why does sulfuric acid have to be on top of the arrow? It doesn't. You might see this instead. Okay, so we have to get used to some variety here. Whether it's drawn any of these 3 ways or this way, it's all the same. Pretend it's a water molecule. You need the H plus to get the reaction to work because water is a weak acid. But to do the predicting part, think of it's a water molecule splitting. The H goes to the carbon with more hydrogens. The OH goes to the other carbon. And we can do a mechanism with any one of those 5 reagents. They all follow the same pattern. Went too far. Go back over here. There we go. Carbocation rearrangements. Okay, so why do they happen? Because nature is following the path of least resistance. So let's follow the mechanism. Step 1, we say the pi electrons go and grab an H plus. So when I draw the mechanism out on an exam, let's pretend I'm a student, you really do have to show that covalent bond. You can't just say curved arrow goes to this H, because then you can't show how this bond is going to break. That's part of the mechanism. The hydrogen gets bonded to the alkene carbon. At the same time, the hydrogen breaks away from the chlorine atom. So this bond breaks simultaneously with this bond being formed to the hydrogen. Okay, and our pattern is copy all the carbons, did that. Pi electrons, that went away, did that. And now the hydrogen has to go to one of these 2 carbons. Well, the rich gets richer. The H goes to the end of the chain. It went over here. Why? Because if you put the hydrogen there, the plus charge goes here. What degree is this carbocation? This carbon, hey carbon, how many carbon atoms are you linked to? I got 1 on my left, 1 on my right. I'm secondary. Nice. If you put the plus charge here, hey carbon, what degree are you? I'm connected to 1 carbon. I'm only primary. Yeah, thanks for not giving me the plus charge. I'm not going to deal with that as well as a secondary deals with it. It can stabilize it better than I. Mechanism shows all the steps, all the details. So what became the chlorine? The bond broke, and we have chloride ion. I'm going to put in the lone pairs. There's 4, because I need 1 of them. Sometimes the chloride then connects to the carbocation. And if you want to put the chlorine pointing up, you can. But you got all this room down below. You know, it's just more stable if you put it down there. That's good. If you want to put in the H, you can. You're drawing it. You decide how you want to draw it. Turns out, depends on the temperature and the concentrations, but this is not the only product. Because sometimes, think about this in real time. You got this beaker, and these are 2 gases. They're bouncing around inside the beaker. Well, maybe a sealed flask, so they don't stink up the lab. They collide. So the pi bond smacks right into this H and steals the hydrogen, and the chlorine goes ricocheting off away from the molecule. And now there's a plus charge in the chlorine here. Well, the chlorine has to ricochet off another molecule and come back. That's not going to be instantaneous. That's going to take some time. Probably a really short amount of time, but it still takes time. And so if there's a chlorine that's close by, maybe we can quench the secondary carbocation and go right to product. But there's other times But the carbocation's like, chlorine, where are you? And this carbon's like, yeah, give me some help. I got 3 bonds here, and I'm only secondary. I can't deal with this positive charge. Help me out. Well, right next door is well, what degree is this carbon? Well, this carbon, hey carbon, how many carbon atoms are you attached to? I got 1 on top, 1 on my left, 1 on my right. I'm tertiary. You're tertiary. Hey, you want to hold on this plus charge for me for a while? Because tertiary is more stable than secondary. The carbon says, all right. Doesn't want to do it, but he understands the situation. So how do we break away a bond? The mechanism says that the covalent bond, these 2 electrons, are drawn to the positive charge. Opposites attract. A bond is 2 electrons. They're negative. These 2 electrons actually connect to the carbocation and drag the hydrogen with it. So what happened? Keep all the carbons in place, but the hydrogen slides over 1 bond. And then this carbon's now missing a bond. There's a carbocation. So you can put the plus anywhere nearby. I'll put it down here. And it made a tertiary carbocation where initially it was secondary. What shifted over? The hydrogen with the electrons. A hydrogen with a pair of electrons, that's a hydride ion. And it's possible to make that in the lab. So the H with the lone pair slid over, a hydride ion slid over. So sometimes this is called a hydride shift. You can also call it a carbocation rearrangement. We had a secondary carbocation which rearranged to a tertiary one. The plus charge moved over. Or more precisely, a hydrogen slid over and created a plus charge on a different carbon. This is a carbocation rearrangement. And yes, you have to watch out for these on the exam to get full credit. Rearrangement. You need to show both pathways, both mechanisms. So, starting at the beginning, pi electrons, grab an H, kick out chlorine, you make this secondary carbocation. The secondary carbocation, same as this one. Sometimes chlorine quenches, reacts with the carbocation immediately to make this product. Sometimes the hydride, the carbocation gets impatient, hydride shifts over to make the more stable tertiary carbocation. And then the chlorine finally shows up. And opposites attract. So now this negative chloride is going to be attracted to the tertiary carbocation, and it goes there. Let's see if I can squeeze it in here. Put the chlorine here, hydrogen's here. You need to draw both products on the exam to get full credit because both are being made in the lab. That's the prediction. Okay, hydride shift is one of 2 possible carbocation rearrangements that you might see. You will see in either the homework or the exam or both. The second type of carbocation rearrangement is the following. It's demonstrated by the following example. Let's keep reacting with HCl, although you know we can use one of the other reagents. Same process. Step 1, hey pi electrons, go grab your H plus. Cool. Copy the alkene minus the pi bond. Alkene carbons were here. The rich gets richer. So the hydrogen, ooh, and I just told you not to do this. I'm gonna miss a point because I didn't get my other curved arrow. No, I want all my points. So I'll redraw the HCl and show that covalent bond breaking with the second curved arrow. Good, got it. All right, hydrogen. You go to the carbon with more hydrogens. Well, this carbon over here has 2 H's. This carbon only has 1. So that carbon at the end is the rich one. It gets the hydrogen. Plus charge goes here again. Chlorine, it's the byproduct of HCl splitting. There's chlorine. And then, yep, if this chlorine is quick, it can attack the carbocation right now and make your first product. The chlorine there. Get these groups there. There we go. That's one product. But if the chloride ion gets lost in the sea of all the other molecules, the solution, whether it's in the gas phase or liquid phase, whatever, well, then it's going to get impatient, sitting here, man, the secondary carbocation is just not happy. Look at this carbon over here. You got 4 carbons. You're quaternary. You want to help me out here? And it says, sure. So how do I want to do this? Let's draw in the CH3 groups. Let's get out of skeletal drawing. And then this is a single bond that's free to spin. So any one of these 3 methyl groups could spin and be close to the carbocation. I'm a visual learner, so I'll explain why in a minute. I'm going to just pick this methyl group, but you can pick any one. This methyl, that methyl. So I'm going to have this methyl group take its electrons and slide over. So really, it's just going to slide across. Just boop, just move on over. The methyl group's going to connect here. So the hydrogen's at the end. This used to be secondary. I got a CH3 here. I got the other CH3 there. Originally, there was a CH3 here, a methyl. Then it slid over and attached to the secondary carbocation. This carbon was quaternary, but it lost the methyl group, so now it's tertiary. And it only has 3 bonds. Here's the plus charge, and now that's a tertiary carbocation. And nature takes a little, that's better. But dang it, where's that chloride? I want 4 bonds to my carbons. Secondary is more reactive, less stable. So while I was waiting, it's not stable, it reacted with itself. The methyl group slid over. It did a methyl shift. And that's the second type of carbocation that could be seen in this class. It's another type of carbocation rearrangement. But I'm going to limit all my reactions that have carbocation rearrangements to these 2 possibilities, hydride shift or methyl shift. It's a carbocation rearrangement. In the real world, you can have other groups sliding over. And I think there's a homework problem that shows that, just to illustrate that it's not limited to methyls and hydrogens shifting over. Not done with the mechanism. This is not the final product. Carbon wants 4 bonds. Well, sometimes the chloride attacks the secondary carbocation, other times it attacks the tertiary. If you want to draw in all lone pairs, you can. If you just want to draw in one, because that's all you need for your curved arrow, I'm totally cool with that. And again, I have to squeeze this all in there. And the chloride goes here. There we go, 2 products again. It is possible to get more than 2. I'll try to limit reactions on the exam to just 2 products, but don't count on that. Take a look at what the reaction's doing. Cool. I hope. There you go. I think that's it for carbocation rearrangements. Nice. Yes. Okay. Last topic. Just want to get started on part 4 of the key concepts. So we'll do one of these reactions and then we'll end the video. So if you have your Canvas website opened up, go ahead and download Unit 2, Part 4. It begins with another reaction, our second reaction, if you will. And think of it as a second reaction, but I'll have students say, no, this is reaction number 6. Because they said, this is really 5 reactions. Okay. So whether you're optimistic or pessimistic, yeah, there's 5 reagents that do this one pattern. So I guess there's 5 reactions. Lighten the load and think of it as one reaction following the same pattern. So I'm going to go and be optimistic and say, I think there's only, this is reaction number 2. Some students like names of reactions. Maybe that's one way to remember these is by naming the reaction. So this reaction is called halogenation of alkenes. Very sciencey again. So take an alkene and put halides on it, halogens on it. So halogenate it. So what we're going to do is not react with HCl or HBr, but Cl2 or Br2. We did free radical halogenation of alkanes. That required heat or light. But alkenes are more reactive than alkanes. Double bonds more reactive than single, so you don't need any heat or light, even though it's using the same reagents, Cl2 and Br2. We're not going to be able to use F2 because it reacts with the container that you put it in. It'll be hard to make it only react to the alkane, so we're just not going to deal with that. And we're not going to use I2 because that's pretty stable. You can buy it in a drugstore. Grandma used to put on my cuts and bruises, not bruises, but cuts and scrapes to sterilize them. Yikes, it stings. But it's not that reactive. You can store it in a bottle. That's not that reactive. It isn't a good reagent for this reaction, so we're not going to use it. So we restrict ourselves to the halides halogenation reaction with just chlorine and bromine. Key points. The reaction occurs with anti-addition. Fancy talk. We're saying if you have a ring, or even if you don't have a ring, in the mechanism, the two halides are going to add to opposite sides of the alkene. That will really matter if you have a ring. If the alkene's in that ring, then the halides actually end up being trans to each other. But whether or not you have a ring or not, the halides are always adding opposite sides. So that's sort of like in the Newman projection, where the biggest groups are opposite. That was anti-conformation. So anti-addition is a process where the two halides are adding to opposite sides, anti from one another. And then you can say, well, what results then is anti-stereochemistry. So I'm providing these terms because you'll see it if you Google this reaction. And I'll use these terms from time to time. So stereochemistry, the three-dimensional shape is stereochemistry. So we have the chlorines three-dimensionally arranged anti to one another. And we need to know the mechanism, the step-by-step process. Okay, so let's take a look at a couple examples to illustrate this. To keep it simple, I'm going to stick with the same alkene as our other reaction. This is 1-propene, and we're not going to react with HCl, but why don't we try Cl2? This mechanism doesn't need Markovnikov's rule. All you do is take away the pi bond, copy the rest of the molecule over, and if you took away the pi bond, the alkene carbons are missing a bond. Well, that's perfect because you have two atoms of chlorine. Each carbon gets a chlorine. Now, because this is a single bond, this chlorine can spin all over the place. When we draw the mechanism, we'll actually discover that if the carbon-carbon alkene, the double bond used to be like this, one chlorine will point up, the other chlorine will point down in an anti-configuration. That's how they add to the molecule. But this molecule is the same molecule as this one, just in a different shape. So if you want to zigzag it, you can. Technically, you're just spinning this single bond so the chlorine pops up here. It's the same molecule. But if you restrict the rotation of that single bond, then the chlorines have to be locked in place on opposite sides. So what if we go grab cyclopentene and treat it with Cl2? Well, you can use Br2 if you want, but Cl2 works, they work the same, they do the same pattern. So the pattern is lose the pi bond, redraw the rest of the molecule. The alkene carbons used to be here. Well, after the pi bond leaves, those carbons only have 3 bonds, they need 1 more each. Well, I'll give them each a chlorine. This time, however, one chlorine goes up, the other one goes down. And you decide which side is up, which side is down. And if you're thinking chirality, good for you. You actually get a mixture of both enantiomers. Now, I'm going to be lenient on exams. So technically, yes, you get a 50-50 mixture of these two enantiomers. Some professors are sticklers saying, you must draw me both of those. I'm a little more liberal, a little more lighthearted. It's important to show that it's trans. You do not make, this reaction will not make the cis isomer. whether you decide to have 2 wedges or 2 dashes. This reaction doesn't create those. The most important feature is that the chlorines add in anti-stereochemistry or anti-addition. It makes a trans product. So I need you to show me one of the trans, and then I'm happy. Cool. All righty. And again, don't use dash and wedge bonds here. Because yeah, sure, one chlorine is up, the other one's down, but wait, up and down is not the same as in and out. Also, if you decide to use wedge and dash, now you're starting to show chiral centers. Now you're implying, well, wait a minute. We put a wedge here, there's 2 H's. Why are you putting a wedge bond or a dash bond there? That's not a chirality center. Okay, so it gets a little confusing. So stick with rings that have wedge and dash. That's where you really have to pay attention to cis and trans. In this case, it'll only be trans. But if you have a chain or branch chain, you don't really have to worry too much about the anti-addition because the single bond that results can freely spin. All righty, what else do we need to know? The mechanism. So we'll end the video with that. Now I was thinking about doing the mechanism twice, but it's getting a little long. So let's just do the mechanism for the cyclopentene. It's the same as for the propene molecule. And then let's also take an edge-on approach. So right now, as I look at this drawing, I imagine myself above the 5-membered ring, looking down on it. Well, let's take another angle and kind of look at the molecule from the edge. So I hope you get the idea that these 3 carbons are away from you and these 2 are towards you. And the molecule about the double bond is flat. And then we're going to start a mechanism. So we need to draw the covalent bond between the 2 chlorines. And the mechanism starts out like the electrophilic addition reaction of HCl with alkenes. Pi bond jumps out, and I'm going to have it come up from the top and grab a chlorine. So I'm implying that the chlorine is going to attach to one of these carbons on top of the ring. And then chlorine is a halide, prefers 1 bond. So as the pi electrons grab the chlorine, it says, well, I would like to only make 1 bond, so I'm going to let go of these electrons, and the other chlorine will grab it as another lone pair. So I'm still going to take the edge approach of my cyclopropane ring now, because the pi bond left. And it turns out chlorine is capable of making 2 bonds, and it does so. It will actually bond to both carbons. And I should probably use wedge bonds, saying, hey, it's coming up and out of the plane here. If we want to count things, this chlorine had 2 lone pairs and a covalent bond to start with. The pi electrons added to it, and this this covalent bond left. So the pi bond connected the chlorine to 1 carbon, and then chlorine used one of its 3 lone pairs to make a bond to the other carbon. And it made a new triangle, a little, well, it's not cyclopropane, but it is a 3-membered ring right here. It did that to prevent a carbocation from forming. Remember, carbocations are unstable. Carbon wants 4 bonds, not 3. And so nature says, you know what? We'll let chlorine make 2 bonds instead of 1, because the more bonds, the more stable. Yeah, but chlorine's like, I only want to make 1 bond. And with an extra bond, it actually takes on a +1 charge, a formal +1 charge. The chloride, the other chlorine, it had 3 lone pairs. It gained another pair from this covalent bond breaking. Now it's a chloride ion. Cool. All right, then what? Well, a couple things. Opposites can attract. The negative chloride can be attracted to the positive chlorine. And if a lone pair connects this chlorine, it can break these 2 wedge bonds and go right back to starting materials. You knew that as a reversible reaction. You don't have to do this on your exams, but technically, the chloride could collide with this and revert back to starting materials. So it is a reversible reaction. But let's move forward. The chlorine can also attack one of the carbons. Wait, I thought it was opposites attract. It is. Then what's attracting the chloride to these carbons? Electronegativity is a source. So who's more electronegative, chlorine or this carbon? Well, the more electronegative atom is close to the fluorine on the periodic table. Fluorine is the most electronegative. It's the bully. It's yanking those electrons better than anyone else. Chlorine is not too far off. It has strong electronegativity too. Carbon's farther away. It's less electronegative. So this bond right here, this wedge bond, consists of 2 electrons, and chlorine is more electronegative. So these 2 electrons are heading towards chlorine because of electronegativity. They're also getting a boost. The chloride also bears a positive charge, and that attracts these bonding electrons even more. So these electrons are really starting to head up here, and carbon's just holding on for dear life. Don't break that bond. I don't want to become a carbocation. But these electrons are leaving and creating significant partial positive charge here. Same problem over here. This carbon's saying, yikes, chlorine, what are you doing? It's electronegative, pulling these electrons away. It's winning the tug of war. This carbocation, it's not carbocation, it's a cation. It's making the chlorine even more positively charged, or it's more electronegative in a sense. It's attracting these bonding electrons even better because of the positive charge. And now this carbon is becoming positive. Which carbon becomes more positive? Well, both carbons are, what degree are they? Talk to this carbon. Hey carbon, how many carbon atoms are you attached to? We got this carbon over here and this one over here. I'm secondary. Hey carbon, how many carbon atoms are you attached to? I got one up here, one over here on the left. I'm secondary as well. If one of these was tertiary carbocations are more stable than the secondary. So the tertiary one could start letting go of these electrons because it can deal with the positive charge that builds up. We'll discuss that in the next video. For now, just realize they're both secondary. They both hate being carbocations. They don't want to be carbocations. Don't let go of that bond. But chlorine is winning the tug of war. It's pulling these bonding electrons up towards it, creating significant positive charge. Well, the chlorine can attack the carbon and make a bond to it. Opposites attract. Should it attack on the top or on the bottom? Well, this chloride is on top of the ring. It's kind of blocking this carbon. It's easier to come in from the bottom. That's anti-addition. There we go. So the mechanism's explaining why we only see trans. It's because of steric crowding. The chlorine sits on top of the ring here. So the chlorine must approach from the bottom to avoid the crowded top part of the ring. And as chlorine comes in and connects to this carbon, this bond then snaps and breaks. Got the periodic table hiding over there. Okay, last step of the mechanism is the chlorine then is attached. So let's draw the cyclopentane ring kind of edge on still. That's awful, sorry, but you see it, I hope. The chlorine came from below, so it's attached below, so it's kind of fading away. This bond did not break. That's a wedge bond, it stays wedge, but because the bonding electrons repel each other, this bond swings out of the way of the ring and gets a little more room over here. There we go. One wedge, one dash, that's trans. Earlier we said, though, you can kind of see it in the top part of the screen, top left part, we said you actually make enantiomers. So here the chloride has a wedge on the left. How do you get the chlorine to have a wedge on the right? Well, let's redraw that molecule. So I'm redrawing this intermediate. The cyclic intermediate with the chloride at the top. That's a wedge bond. Ooh, that's a big wedge. Doesn't matter. Chloride is over here with its 4 lone pairs, attracted the positive charge that's building up on the carbons. Okay, sometimes the chloride might be on this side of the ring. It'll come in from the bottom. Again, it doesn't come in from the top because the chloride is blocking the top of the ring. So chloride could either attack the right carbon or the left one. They have equal amounts of charge. Just depends, statistically, just randomly. How's this chlorine? Is it coming in from the right side or was it coming in from the left side? Maybe it'll strike this one. If it attaches here, that breaks this wedge bond. And this bond on the right doesn't change. The chloride remains attached to this wedge bond and ends up on the right carbon. So this one stays wedge. It just swings over here. The chlorine still attached to the wedge, swings over, sticks up here. The incoming chlorine came from the side opposite. That's anti-addition. It adds anti or opposite the other chlorine. Comes in from the bottom. It'll end up on a dash bond. There we go. We have a pair of enantiomers. Cool. Let me double check. I think that's it. No, you know what I forgot? There's a quick little guideline about carbocation rearrangements. So remember we had these 2 possibilities, hydride shift. That happened when you have a carbocation and next door is a tertiary carbon. The hydride will shift. If you have a carbocation with a quaternary center next door, you get a methyl shift. So that's our guideline. So for my exams or the homework, here's what you need to know about carbocation rearrangements. Well, first of all, you got to include all the products. So think carbocation rearrangements. You guys are going to start disliking carbocations because they can rearrange. The reaction with Cl2 did not make a carbon with a positive charge, no carbocation. So this molecule up here, went too far. This reaction, there's no C with a plus charge. No carbocation, that means no carbocation rearrangement. Yay. This one had a carbocation, ooh. So anytime you make a carbocation, check the adjacent carbons. If you see a quaternary center, you could get a methyl shift. Up here, we made a carbocation, check the adjacent carbons. This one's primary, ooh, that's not good. This side's tertiary, ooh. If you have a tertiary carbon next to a positive charge, you could get a hydride shift. And that's what I got summarized down here. It's also in your key concepts. To predict carbocation rearrangements, find out first if the carbocation is primary or secondary. Because if it's already tertiary, why rearrange? It's already the most stable carbocation. I just made a little fib there. Today, the tertiary carbocations are most stable. We actually will see later there's other carbocations that are more stable. But for now, of primary, secondary, tertiary, and methyl carbocation, tertiary is the most stable of those 4. That's not a fib, that's not a lie. So first check and see if the carbocation is already tertiary. If it is, no rearrangement for my exams. But if the carbocation is primary or secondary, ooh, you might have a rearrangement. So what do? You check the adjacent carbons. So, if you had we had a positive carbocation that was secondary, check the adjacent sides and, ooh, I just put a tertiary carbon over here. If you have the adjacent carbons tertiary, then the hydrogen on that tertiary carbon will slide over and do a hydride shift so that you make a tertiary carbocation. The other possibility is that if you look at the adjacent carbon and it's quaternary, so the plus charge is here, secondary, and you have an adjacent quaternary center, that's when you can get a methyl shift. And I can hear you guys already asking, what if the chain has other groups on it? Well, on my test, I'll make sure the quaternary center has at least one methyl group. And let's just shift the methyl group. So this methyl group will shift. And then if this leaves, this will become tertiary, and that will bear the positive charge. And tertiary is more stable than secondary. The carbocation is more stable. And then if you don't have those two cases, so let's review the cases. Your carbocation is either primary or secondary. If you look to the left and right of it, if there's a tertiary center, yes, you can get a hydride shift. If you have a quaternary center adjacent to it, then yes, you get a methyl shift. But if the adjacent carbons are not tertiary or quaternary, you do not get a carbocation rearrangement. Yay. That's true on my exams. Hey, but chemistry majors, nature has lots of exceptions. We won't see those in my class. Okay, thanks for sticking around. I'll see you in the next video.